Hello, 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 hello. So there is some leftover material from last class. I'm going to use this part to explain this theorem, a connected graph. Connected graph G with at least three vertices has this graph has no cut vertex. If and only if for any two vertices uh, there are at least two disjoint. So here I want to say a vertex disjoint paths connecting them. Okay, so it's something like this. So if we have VW, there will be at least two paths connecting them, and this path do not use any vertex twice. Okay, so the paths are vertex disjoint. So it has no cut vertex, means exactly means vertex connectivity is at least two. Okay, so this part is pretty clear, but I still want to explain. So I mean this direction is pretty clear. For example, what we want to do, we have that for any two vertices, there are at least two vertex disjoint paths connecting them, and we want to show that the graph G is has no cut vertex. Okay, so what we want to do? Actually, we want to show that G minus V is connected, right? So there is no vertex V such that G minus V is disconnected. So we want to show that for any V, for any vertex V, G minus V is connected. This is what we want to show. Okay, so right, I think this is pretty clear because we want to show this. We can take any x, y in this graph. Okay, of course these two vertices are also vertices of G. So remember, in the original, since in the original graph G, we have at least two vertex disjoint paths connecting x and y, and only one of them possibly contains V. So let me read this. So there are, by assumption, there are at least two vertex disjoint paths connecting them. So it means that one of these passes, one of these two paths does not contain V. I mean in the original graph. So this particular path, which does not contain V, is a path in, so it implies it is a path in G minus V, right? So x and y is connected by some paths in G minus V. Because we take x and y arbitrarily, So G minus V is connected, right? So that's it. So the other direction is a little more complicated. So let me show this. So it's a kind of induction. But before that, let's make a small definition. We define this d of xy for two vertices. The length of the small, it basically is the distance of x and y. So in the graph, if you consider the set of all vertices, you can actually define a metric, a distance. So basically, it's a very natural. It's just you draw the path between two vertices x and y, and it is the shortest, the path, the size of the shortest path is the distance. So for example, if I have an edge, we say that x and y has distance 1, right? This case, this is distance 1. You probably you have this situation, and you see that the shortest path, there is no edge between x and y. So the shortest path between x and y has length 2. You say that distance of x and y is 2. That's the definition. So so it's a length of the shortest path between x and y. So in particular, if x and y is not joined by any path, so okay, let's say it is the shortest. Okay, the size, the length of the shortest path between x and y. Okay, and I want to stress if there is no such a path, means that x and y are disconnected. Okay, there exists no path connecting x and y. In this case, we just define dxy to be infinity. Okay, so it does not violate generalized axioms for matrices, matrix. Okay, so we still call this distance. So it's not hard to see. So we would like to induct. So in order to prove this, we assume that the graph has no cut vertex, and we try to show that for any two vertices, there is at least two vertex disjoint paths connecting them. This is our task. And we would like to induct. We make induction on distance of x and y. Okay, because we want to prove that any two vertices sort of satisfy some property, right? We prove this by induction on the distance of x and y. It's a little surprising, but it's very interesting. The proof is very interesting. So the base case is what? The base case is distance of x, y is 1. Okay, so this is the base case. There is an edge between x and y. Okay? Great. I think this is very easy to check. Okay? Because there is no cut vertex. So in particular, y is not a cut vertex. So G, so easily checked. Because G minus y is connected. Because y is not a cut vertex, G minus y is connected. So you have something like this. Not quite. Let me see. Okay. So probably I need okay. So how to? So it's not. I realize it's not precise. So I mean, looking at XY edge, Okay, so because the graph has at least three vertices, so at least one of them is also joining another vertex. But I'm not writing down everything, okay? I'll speak slowly. So because G has at least three vertices, and G is connected, so there is at least some Z it joins Y or X. So I mean the whole graph cannot be this edge. So at least locally I have some Z such that this happens. So maybe Z joins X, but doesn't matter. So there is no difference between X and Y. Now I can do this. So G minus Y is connected, so X will join Z in G minus Y. So there is a path. Maybe we call P such that X will connect to Z through P. Then we see that XY and XPZY, okay, XPZY are two paths, vertex disjoint. Okay, so this finish the base case. So check the base case. So now by induction, what's the next step? We want to suppose the distance of X and Y is K. And also suppose we already proved that the conclusion is true for all pairs with distance smaller or equal than K minus 1. Okay, so let's fix a path from X to Y. Okay, so this is a path P of length K. So fix a path from X to Y of length K, because the distance is K. So there is at least one such path. And I want to put this vertex I call V. Maybe I call Y, Y prime. Because I want to say something about it. So this is the final neighbor of Y along this path. So next step, we arrive at Y. Okay, so it's called the predecessor of Y. Okay, so in particular, I think it's very clear that distance of X and Y prime is K minus 1. You cannot find a path from X to Y prime with distance smaller than K minus 1. Because otherwise you follow that path until Y prime and you go one step further, you arrive at the vertex Y with a path smaller, shorter than K minus 1, shorter than K. Okay, so I think it's clear. The distance of X and Y prime is K minus 1. Okay, so by induction, we know that by induction hypothesis, we know that there are two paths, P and Q, vertex disjoint, okay, from X to Y prime. Here we have to be careful because probably there is a possibility that the point Y, there is no such possibility, but we have to think about it. I mean, if Y belongs to P, for example, it cannot happen, okay? It means that X along P arrive at Y is a path smaller than K minus 1, so it cannot happen. Okay? So Y does not belong to P or Q. Right? So good. So we have two paths. Okay, what's next? So I'm going to find another path R. Wait a minute. Right. What is the path R? I'm sorry. I'm trying to find another path R. Right. We are using. Okay, great. We haven't used the assumption that y prime is not a cut vertex. So G minus y prime is connected. Okay, so implies there is another path R. There is a path R which connects x and y in G minus y prime. Okay, so this path R does not pass y prime and it arrives at y. Okay, this is R. Okay, so there are little more. There are many objects. So here is x, and here is y prime, and here is y, and there is a path P from x to y prime, and here there is a path Q from x to y prime. Okay, and there is another path R from x to y, and it avoids the vertex y prime. So I found this point, which I call, for example, Q. Okay, so let Q be the final vertex of intersection of the path R with the union of P and Q. Okay? After Q, the remaining part of the path will not intersect P or Q. Okay? Okay, so we have enough things at hand. So, for example, this Q belongs to the path Q. Okay, this point Q. So, for example, we can take Q to belong to Q. So we are trying to find the two paths. The first one is x follows Q until Q. So let me write red. So x follows the path Q and arrive at the point, the vertex Q, and then it follows this part. So after that, it follows R and Y. Okay, so where is what? Okay, R. Okay, R and row at Y. Okay, so the second pass will be the pass P xp to Y prime and then a row at Y. So got two paths. Okay. So this finishes the induction. Right. So this is a very important theorem. We probably will come back to this in a more general form in the later part of this course. But at this point, I found this induction by distance is very interesting. So I put this theorem.